Okay, I'm going to resume the explanation for section 8.3. So today I'm going to cover from example 5, which is about the tangent and the secant. So here's some review, just a review. Derivative of the tangent function is equal to secant square. Derivative of the secant x is equal to secant x times tangent x. So you see tangent and secant are kind of have a good connection. Also, this is not related to integration or differentiation, but the Pythagorean theorem states 1 plus tangent square of x is equal to secant square x. Okay, so please keep these in mind. これ3平方ね。これ3平方ね。Now, example 5 is the integral of tangent x to the power of 4th. Okay. So that looks complicated, but the idea is you are going to try to make secant square or secant times tangent or some mixture of those. Okay. First of all, let's rewrite this one as tangent square times tangent square. Okay. Even is always not easy. Even is not easy at all. Now, tangent square using this Pythagorean formula, you can change into secant. Okay. After expanding this, you will get tangent square x secant square x minus tangent square x dx. Okay. How do we integrate this one? This is easy now because we can change it into secant square. ここでもう一回、secant にね、直せば、So using the Pythagorean again, it's going to be secant square x minus 1, and both of them we can integrate quickly. Okay. Integral of secant square x is equal to tangent x. So that part will be done. So integral of this is going to be tangent. Integral of 1 will be x. So now all we need to do is how we deal with this part. Well, this is not so bad because this part is the derivative of tangent. So you have a function of tangent here, and here is the derivative of tangent here. So you can use a u substitution where u is equal to tangent. Then du will be secant square x dx. So after you do this u substitution, it's going to be u square du, which will be 1/3 u cubed. Okay, so bring back to the original expression. So it's going to be 1/3 tangent cube x minus tangent x plus constant. Okay. 今のは4乗だったけども、じゃあ3乗とかだったらどうするか。Well, let's split into one tangent and two tangents. This can be written like secant square x minus 1 again. And you can split into these two. Now, this part, we can use the same idea. So let's say this is equal to u, then this is equal to du. So that's going to be 1/2 tangent square x. Integration of the tangent is something you might want to memorize. It's going to be negative ln of cosine x absolute value. If you do not memorize this one, rewrite the tangent as sine over cosine. And you use a u substitution for u is equal to cosine x. And you can integrate this one as well. So you see that the idea is break down the tangent into square and the remaining and change it into this, okay? So if you can do integration of the tangent, tangent square, tangent cube, tangent to the fourth, then you probably can do, like, for example, tangent to the seventh or maybe fifth. Okay, so I'm gonna just do fifth. Okay, so this is same thing as tangent cube times secant square minus 1. And the first part can be integrated by making u is equal to tangent. And this part has a lower degree, so you can integrate by following this again. まあ、全化式的な。つまり、タンジェントのパワーがこうあったら、そのうちの2個をシーカント2乗引く1に直すと。そうすると、この最初の部分は、まあ、こんな感じで、さっさとタンジェントのね、形で積分ができる。で、残りの部分は確実にね、元の式に比べて次数下がってるんで、まあ、3乗、4乗までできてれば、まあ、一応計算すればできるよねってことですね。面倒ですけどね。Okay? 今の方法で3乗、4乗ができてるんだから、5乗もね、3乗に落として完成。6乗も4乗に落として完成。まあ、以降それの繰り返しになります。So that's how we integrate the tangent. Next one is a very difficult one. How about secant? What is the integral of secant, first of all? シーカントのね、積分自体がそもそも難しいんですよね。これね。これは、どうやってこれ積分するか覚えてますか？ So, this is actually a very difficult one. In the Pearson's textbook, it's gonna use a magic like this. Multiply top and bottom by secant plus tangent. But that's the magic. Yeah. Can you come up with this idea? Now you see the derivative of the denominator is on the numerator. Derivative of tangent is secant square x. And the derivative of secant x is secant tangent. So this is actually of the form f on the bottom and f dash on the top. So the antiderivative of this is ln of absolute value of f. まあ、分数式でよくね、こうだったらいいなっていう分母の微分が分子という形になってるんで、ln ですねっていうふうになります。 まあ、こんなん気づかねえだろ、普通っていうね。こんなん気づかねえだろって知ってなきゃできねえだろっていうテクニックですよね。ということで、まあ、これがアメリカの教材でのやり方になっています。So, integral of secant is actually much harder than integral of secant square. Yeah. In contrast, this is easy. This is easy. Ridiculously easy. Because this is antiderivative of. Yeah, this is easy. いや、2乗がついてると簡単っていうね。何これこれ何なのって感じですよね。OK。ちょっと脱線になりますけど、日本式にはこれどうやってやるのって、そもそも日本ではシーカントっていう記号を使いませんから、問題で出てくるとしたら、コサイン x 分の1っていう式で積分することなんでね。これどうやってやるのと。どうやってやるのっていうと、これはね、もうちょっと、まあ、わかるかな。手順としてはね。これは上と下にコサインをかけます。上と下にコサインをかけるんだったら、まあ理解可能な手順だよね。まあ理解可能な手順だよね。で、ここで、コサインの2乗をサインの式に書き直します。そうすると、サインの式かけるサインの微分という形になってるから、まあ、ナチュラルな置き換えとして u イコール sinx っていうのが出てきます。Then du is equal to cosine x. And so this becomes 1 minus u square du. cosine x dx がまとめて du になります。How are we going to integrate this rational expression? We are going to use a technique called partial decomposition. 部分分数分解とかいうね、テクニックを使って、これを分解すると、まあ、こういうふうになります。まあ、これは通分の逆なので、まあ、通分してみればね、合ってることは確認できるかなと思います。and 微分ね、分母の微分が分子っていう形になっているので、we can take integration quickly. And well, first one gonna be ln of 1 minus u minus. And the second one will be ln of 1 plus u plus c. So you can combine ln into 1, so 1 plus u over 1 minus u using some property of log. And finally, bring back to x. So it's going to be 1 plus sine x over 1 minus sine x. ということで、まあ、これが答えになるんですよ。いやさっきと全然見た目違うよね。そう、見た目は全然違うんですよ。見た目全然違うけど、これ実はイクイバレントです。イクイバレントになります。余裕がある人はですね、ぜひ、please show why they are equal. まあ、イコールになります。So, the Japanese technique is more understandable. まあ、木をてらった手順は特になく、まあ、せいぜいで最初の上と下にコサインをかけるってとこぐらいだよね。まあ、木をてらったところはないんだけど、しかしこの積分めちゃくちゃ時間かかるねっていうね。アメリカンスタイル、4 lines, short, very short. しかし最初のこれはね、ちょっとこれ覚えてないとちょっと無理じゃねえのって思っちゃうんですけどね。はい。はい。Anyway, just learn one of them at least. Yeah, make sure you can solve it in one way. And that's enough. Okay. Now, example 6 comes after those two. So, integral of secant cube. はい。これ、どうするっていうね。これむずいです。こんなん気づくかよっていうね。はい。So, first of all, split this one into secant and secant square x. And we're gonna use the integration by parts. F1 g dash. Okay. we know how to differentiate this, and we know how to integrate this. So we put secant x here and secant square x here. So the derivative of this one will be secant x tangent x. Integral of this one will be tangent x. So after you do the integration by part formula, the first term will be secant x times tangent x minus integral of secant times tangent x squared. Is the program getting simpler? Not really. Not really. It's still a cubic expression. It looks complicated. But here, I'm going to use the Pythagorean theorem to change it into secant. So the tangent square is same thing as secant square, x minus 1. Now you see what? Now you got the secant cube again. Left hand side was secant x cube dx integral. Do you see this is equal, same thing as this here, dx. So let's say this is equal to I. Then you can combine these terms in the left hand side. So 2i is equal to secant x tangent x plus integral of secant x dx。ちなみにこれはさっき紹介したわけわかんねえ上と下にシーカントかける単をかけてね、積分してこうなるっていうのは示しましたね。So, that equal to twice as many as the one that we want to get. So, the integral of secant cube is equal to 1/2 times this. Do you see how tough this is? こんなん思いつかないでしょみたいなものをオンパレードですね。じゃあまず、1乗と2乗に分けるのはまあ置いといて、そこからね、タンジェントに直すとかじゃなくて、ここでね、部分積分やると。で、部分積分やった後に単をシーカントに戻すと同じ形が出てくるよと。ということで、あとはシーカントの1乗の積分ができればいいんだけど、それもそんなに簡単ではないんでね、もうこんなの覚えてなきゃできねえだろうっていう感じです。はい。はい。ということで、そんな流れになるよねっていうことですね。はい。もうシーカントの積分はアメリカの教材では、一応シーカントって基本式の一つだから、もう公式としてね、もう当てはめちゃっている感じですけど、日本だと、公式化されてないので、頑張って上と下にコスかけてっていう手順でやることになるから、こんな問題が出てきたら、日本式でやると相当時間かかります。コスの3乗分の1のね、積分が出てきたら、はぁとかってなるでしょう。はい。なります。Okay, next example. Example 7. Tangent to the fourth, secant to the fourth, dx. Well, looks complicated. But its even power is probably nicer than secant cube. So one possible idea is using 1 plus tangent square x is equal to secant square. And so we can convert one of them into tangent or to the secant. So remember, the derivative of tangent was secant square. So secant square is nice to leave it. So we don't want to have 4 of them. But if we have 2 of them, that's nice. So first of all, break down secant to the power 4 into 2 and the rest. 2 and the rest. Okay. And this is equal to 1 plus tangent square x times secant square x dx. Now this is good. Now this is good because this is in terms of tangent and this is derivative of tangent. So let's say u is equal to tangent x, then du will be secant x squared dx. So after the substitution, it's going to be u to the power 4 times 1 plus u squared times du, which is very easy to integrate. It's going to be 1/5 u to the 5th plus 1/7 u to the 7th plus c. Bring back to the x, 1/5 tangent x to the power 5 plus 1/7 tangent x to the power 7 plus c. Okay, so that's how we handle this kind of expression. So like the one for the sine and cosine case, when you have even powers, leave secant square and make everything into tangent. If you can do that, that's good. Another idea is make everything in terms of secant and secant times tangent. Okay, so when you have odd number of tangent, this might be useful. Because when you have an odd number of tangent, well, for example, when you have a tangent cube, you can make 2 of them into secant, and you can leave 1 tangent. Okay, but you have to leave, the hard part is you have to leave 1 secant and 1 tangent. So if you can do that, then that's another way to integrate this kind of expression. Yeah. Okay, so that's the kind of general idea. Okay, one more thing in this section is about the product of sine and cosine, which is looks like sine of some linear function times sine or cosine, doesn't matter, of some linear function. Okay. When you have something like this, there are 2 ways to do, and one is the integration by parts. If you do the integration by parts by putting f for this and g dash for this, and if you do it twice, if you repeat the technique twice, you're going to get back to the original integration. So that's one way. Another way is probably much easier, is using product to sum formula for the trigonometric function. So using that, you can split into the sum, and that makes it much easier to integrate. 積和公式っていうのを使えば、掛け算されている式を足し算にすることができ、まあ、足し算系だったら積分は別々にやることができるので、それで処理することができるよ。So I really don't remember the formula for the product sum, but here it is. Here it is. So once you rewrite the product into sum or difference, it's very simple to integrate. When you have like 3x and 5x, it's no problem. But if it is say mx and nx, you have to be careful when m is equal to n. m と n で書かれている場合は、m と n がイコールの場合だけちょっとサイン、コサインにならないので、要注意になります。はい。だからその場合だけね、ちょっと場合分けで考える必要が出てきます。Anyway, well, key idea is just the product sum formula. Page 1. Okay, so there's just one example here. So I'm going to just show you how I will do this one. Okay. So example 8. The integral of sine 3x times cosine 5x dx. So let's use the product to sum formula, which I really don't remember much, but 最多コスモス系なんで、サインの加法定理からスタートします。So sine A plus B is equal to sine A cosine B plus whatever. And sine A minus B is equal to sine A cosine B minus whatever. So if you take the sum, this part canceling each other, and you want to get 2 sine A cosine B. So that's the product to sum formula after you divide both sides by 2. So now you use A for 3x, B 5x. This integration becomes 1/2 sine 8x plus sine minus 2x. Now this is very easy to integrate, but I hate negative in front of inside the sine function. So let's use a property of the odd function of sine to make negative outside. Remember, sine of negative theta is equal to negative sine theta. While cosine negative theta is equal to cosine theta, so you have to be careful about the difference. Now you can integrate it. Integral of sine will be negative cosine. So it's going to be cosine of 8x, but you have to divide it by 8. And this one will be plus 1/4 cosine 2x. And don't forget to add c. So that's how we handle this kind of expression. I'm going to show you another method, which is the use of the integration by parts. So let's say this is f and this is g dash. Doesn't matter which is which. So I'm going to just write down like sine 3x and cosine 5x. Derivative of this is 3 times cosine 3x, and derivative of that one is going to be minus 9 sine 3x. This one you have to integrate. Integration of cosine will be sine, but you have to divide it by 5. And integration of sine will be negative cosine. So it's going to be cosine of 5x, but you have to divide it by 5 again. Okay, so let's say this is equal to I. Then I is equal to this 1/5 sine 3x cosine 5x sine 5x plus this plus 3/25 cosine 3x cosine 5x plus integral of this one, which is integral of 9/25 sine 3x cosine 5x dx. And this is equal to I times 9/25. Okay, so this is same thing as 9/25I. So bring this one to the left side of the equation. It's going to be 16/25I is equal to this piece. Okay, so I is equal to 25/16 times 1/5 sine plus 3/25 cosine and plus integral constant c. So that's reduced to 5/16 sine 3x sine 5x plus 3/16 cosine 3x cosine 5x plus c. Okay, so that's maybe harder, probably harder than doing a product to sum formula. It's definitely more steps to do. And you see that answer looks quite different. Answer looks quite different. Wow, what's this? Yeah, looks quite different, but they are same. They should be same, okay? And I will show you why they are same. So I'm just copying the answer here. So it's going to be 1 negative 1 over 16 cosine 8x plus 1/4 of cosine 2x. Are they equal? Cosine 8x is same thing as cosine 3x plus 5x. Cosine 2x is same thing as cosine 3x minus 5x. Now you can use the additive formula identity. So this is going to be cosine 3x cosine 5x minus sine 3x sine 5x. Do the same here. It's going to be cosine 3x cosine 5x plus sine 3x sine 5x. Now you see this is a like terms and they are like terms. So we can combine them together. So it's going to be 16/3 cosine 3x cosine 5x. And this one going to be 5 over 16 sine 3x sine 5x. So it's identical. So although they look quite different, but they could be shown to be identical. Well, I don't recommend you to solve this way many times because it's kind of tedious to check your answer with the back of the textbook, because back of the textbook probably have only one solution. But it's good to try it in this way and try to show your answer is actually identical with the one shown on the textbook. So that's complete explanation for section 8.3. And next time I'm going to start explaining section 8.4, which is the integration of some complicated expression with radicals, but we can solve those by quite smart substitution by trig functions.